physics, MMLP2. This will be a small program, 6-1, over 24 months in total. Marrow of mapping machine learning to physics is the use of logic applied to the electric properties of machine learning to constrain the objective space, and the creation of multi-objective functions to set the optimal trade-off between joules of energy and model performance. Coupled, these tools enabled principled, computationally efficient construction of energy-aware ML. And I'm Bernie McShay. I'm the program manager. And here we go. So we want to redefine power as the first-class citizen throughout the machine learning lifecycle. When we start on the left-hand side and move down the pipeline from training data and how it's collected, what is collected, hardware that's going to be used, the machine learning algorithms to marshal the data, the training, and the inference. We want to create energy-aware machine learning. This is machine learning, which is optimized with respect to power for the lifespan of the machine learning model. So this is data set selection all the way through model inference while retaining performance. So in the instance of classification, this would be accuracy, precision, recall, and F1. The hypothesis that we're testing in this research is that power consumption and performance of machine learning models on existing hardware can be improved by preserving local energy semantics and creating tunable multi-objective functions to create energy-aware machine learning. So we're not creating new hardware on the program. We are more efficiently using the hardware we have. But we will talk in a little bit moment on this further. On the left-hand side, machine learning on the edge with respect to battlefield conditions is something that the DoD is interested in. So we have to imagine that there's additional constraints to just being machine learning on the edge. So any model which you have as effective, obviously there's an incentive to what is naturally considered like concept drift. You want to make the other person's model less effective. So we're going to have to retrain. This is something we just have to take as a assumption here. There's a high operational tempo. So with the equipment you have to make the best use of it quickly and locally. And the way we do machine learning on the edge today is to take lots and lots of data, use racks of servers, do a lot of computation, and then bring this either to FPGA or ASIC circuit and do quantization, model pruning to make the model smaller and more efficient, and then ship it out. But we have to consider that there might be a jammed environment, so moving data around might be an issue. And you might not have full freedom of movement as well. So moving equipment around might also be an issue. So what's needed is we need to extend the warfighter's existing capacity. So by using less energy, we're going to extend battery life. Here, the crux of the program is to provide a theoretical basis for energy-aware machine learning, software, and hardware. So we want to create a way of doing energy-aware machine learning on existing hardware, but do so in such a way that we can predict model usage on hardware, enabling further hardware design. So it's out of scope to build hardware, but we're keeping our eye on the theory that we're making it useful for further experimentation or usage. On the right-hand side, this is a very simple diagram, just denoting that today, when you train a model, we actually don't know its accuracy and we don't know its power usage. And what we really want is the capability of knowing what the economy, both in cost and performance, of the machine learning we're about to produce. So MLP will map machine learning performance to joules of energy, associating machine learning to physics. You can't outrun the laws of thermodynamics, and we want to be able to compare across hardware architectures and types. So we're very expressly mapping joules of energy, watt-seconds, electricity in this program. Today, all previous hardware and software design choices are discarded after each step in the machine learning pipeline. Starting on the left-hand side, when we have the data set, so that little square D underneath, and we have the design choices for the hardware, each one in this case, and we move down the stream in the pipeline, we're not preserving that. So how we collect the data, what data we collect has vast computational implications downstream. Give a quick example of this if we're talking about autonomous vehicles. Do we collect camera data? What resolution do we collect? Do we collect the color channel or not? You can identify a stop sign by its shape and the letters, obviously, but the color channel also plays in for some information. What is the electric cost of that? When you exclude this, what do you mandate goes on for further computation to have the same level of accuracy? So these effects that are taken upstream have downstream effects. And not having LiDAR, for instance, that means fog and other conditions are an issue, and the computation isn't there because the imagery isn't there, right? The sensory data isn't there. And also for hardware, obviously when you design hardware, there are a vast number of considerations, and there's a lot of fundamental trade-offs. The more electricity you put into a board, especially depending on where it is in the layers of the board, dispersing heat becomes a significant issue. So there's a lot of trade-offs here. The size of the memory in relation to the CAS, whether you have a clock, whether you have an ACK-NAC protocol, the locking conditions. There's many design decisions that go on. So today we don't preserve all of that as we design algorithms further down. So it's a little hard to see on this slide, but we have little gray silos here. So we're doing localized optimizations today. There's a lot of wonderful research on doing optimization. Yeah, so we are also optimizing solely for performance. We're not doing multi-objective optimization. And again, we're missing or disregarding the design choices that this impedes further hardware design in the future. All right. We also need a principal way of constructing software to fully utilize available hardware today. So on the left-hand side, from the paper Liu et al., they demonstrated a 7 times decrease in inference time by training a model on an NVIDIA Titan GPU and then quantizing this and then bringing it over to an Intel Aria 10 FPGA. Obviously, they wrote the inference fabric to run this as well. And we know that the Intel Aria 10 uses less electricity, and we used it for less time, so we can assume that it used less energy to do inference. But on the right-hand side, the way it's done today is empirical. So we do lots of experiments, and then we pick the best one of the set we did. What's needed is a principled way of doing this. We need to preserve information to do this. So a test that I don't believe was run was if you quantize during training, would that have been more efficient? So there's always another parameter or something in these experiments you can tune. We're missing a principled approach. So the bottom bullet on the slide there is that successful empirical findings are not sufficient to informed principled constructions as information loss may not be fully rediscovered. So, today, we're missing a principled way to compare hardware performance for machine learning. So when we strictly look at top watt scores, there's a lot of relevant information which isn't being captured. So on the left-hand side, the article titled Lies, Damn Lies, and Top Watts. Highlighted in white is all the information we preserve, and grayed out is all the information we're not preserving in that top watt statistic. So this results in, on the right-hand side, the gaming of lots of metrics. So if we have a multiply accumulate operation, that sounds like 2 operations to me. I can double my top watt score by counting. Oh, there it went. All right. All right, I'm going to continue. All right. So there's unspecified optimistic operating conditions. So the temperature in the room when the top watts were taken is another factor in this. The amount of electricity and the nominal voltage applied is another factor. There's overstated utilization rates. If I run the system at 50%, well, I just assume I have a perfect system that runs, but we don't take into account locking, swapping and other conditions that happen in a real system. So that top watt, we just presume perfect efficiency in the way that it runs, right? Batch size manipulation as well. So you can do smaller batch sizes. It has latency implications, but it's not captured in top watts. So for H3, so this is the what is new about your approach and the Hellmeyer questions. Mantra of the program is preserve, tune, and optimize. We want to preserve the local energy semantics. So that's the little green arrow there. So we'll notice as we go downstream, we're keeping all of the information that we had prior. And the reason that the arrows are two-wayed is we want to study and come and reason over the energy semantics to discover interactions. So what are the upstream design choices that limit the objective functions and optimizations we should be considering in the future? So when we make a decision about the training data, kind of that we discussed earlier, what algorithms should we not be considering, and what are the implications? And we want to understand this two-way aspect. So we want to study these interactions of energy-aware semantics so that we can preserve this and reason over it. Also, we want to create tunable objective functions. So we want to do a multi-objective function where we're doing joules of energy and the model score. And this is so we can intentionally set the optimal trade-off bias. So pictured here is the classic Pareto frontier. So we have feasible and then infeasible, and right on that curve is the intended optimal trade-off between them. So we can set the bias for what we're working with. Yeah. We want to be able to inform hardware design by the energy semantics and the reasoning we had done over the optimizations. So again, the mantra of the program is preserve, tune, and optimize. We want to preserve the local energy semantics, create tunable objective functions, and then optimize the machine learning for each stage of the machine learning. So starting on the left-hand side, we want to discover and preserve local energy semantics. So the way we're going to do this is by taking accurate granular measurements of power and the energy semantics, preserving this information. This is the first part of the program that we have the logic and we've informed it by the physics. Yeah, so on the bottom of that chart, we'll see a picture of the NVIDIA power capture analysis tool. We have video gamers to thank for their NVIDIA's debugging tools being commercially available. So wanting to play video games at a good resolution, but also using a sufficient or a low amount of power, you can measure at the OS, but that doesn't have that granularity. NVIDIA offers the ability to check on the card the power usage. That's not granular enough. Video gamers insisted on having higher fidelity, so this was released. So we have a tool here to do it. Pictured next to it, this is courtesy of Mukund, the program manager for the DARPA Knapsack program. This is a photonic circuit for capturing the joules of energy used for a neural net in photonics. The MMLP2 program is not specifying the hardware that can be used. If you have access to it and you can provide it to the test and evaluation team to be independently verified, you can use whatever hardware you'd like. But joules of energy is what we're considering. And I'll make the point here that the granular measurements and the precision and the comprehension of what that means and doesn't mean is really important. So in my career, I've come across what I refer to as capital F forensics and lowercase f forensics. So capital F, we want to think of forensics that's used in the criminal justice system. So in there, there's a lot of rigor of what can be used, when it can be used, and under what circumstances. So for instance, there's a Federal Rule 401, test for relevant evidence, 703, basis of expert, 901, authenticating and identifying evidence. So these culmination of very stringent standards and having a defense also make sure that the evidence presented is accurate. The laboratory that it was done needs to be certified, an ASCLD certification. The instrument is the calibration of the instrument, the person who did the exam, what it proves, what it doesn't prove. So it's very, very specific about what can be done. And we need to think of evidence in this way as like a single stroke of a brush or a single color that we're painting a picture with. What I refer to as lowercase forensics is when we have a tool that is principled. And in this case, I've seen varying degrees of stringency about understanding what it does and doesn't cover. So just to provide a brief example here, if you have a network PCAT capture, you can say that it was observed at a certain time, but the time was taken from where? Was it taken from the switch or wherever this PCAP was captured? Is that the true time at the time, right? The email correspondence happened, you can say it went from one IP address and MAC address to another. You can't say who was at the keyboard of the computer. That evidence doesn't provide that clarity. So being very precise about what is and isn't provided, since this is the cornerstone of doing what we reason over for constraining the objective space, meaning we're excluding possible performance and options based on these readings, right? So this is why I'm very adamant about being forensically, capital F, forensic accurate in this. So moving to the right-hand side, we want to also then have tunable objective functions where we set the optimal trade-off. So the green star in the middle is a balanced set of bias, but we want to be able to set that wherever we want for getting the results of power and performance. I'll come to make a sharper point on the next slide here. And then finally, we want MMLP2 to construct energy-aware machine learning with optimal joules of power and performance for a given task, clustering, classification, generation, with a candidate set of hardware for a point in the model's life cycle. So coming to the objective functions. So we described that proposers will come with a set of hardware. They will describe how they're going to forensically measure things. And here we're describing that the objective functions that we're going to consider to become multi-objective functions. If we think of this on the left-hand side as a toolbox for doing machine learning, each drawer being a type, regression, classification, clustering, and so on. When you open the drawer at the heart, the tool is actually a mathematical function. So if we consider B of X being mean squared error or cross-loss entropy, and there doesn't need to be an exact linear mapping, you could do cover two existing tools with a new function. We want to create a multi-objective function where we're minimizing joules of energy and loss, and that is B prime of Y. This gives us a new toolbox where we can create energy-aware ML and intentionally balance the performance and the power usage. So we're asking performers to come with what is the toolbox that you're going to fill? Why is that providing the degree of coverage that is necessary to be useful and relevant? And what is your methodology for doing this, right? Okay, so kind of putting together the task and deliverables. Starting on the left-hand side, so how we're developing capital F forensic instrumentation to sample the power, because this needs to be done granularly and in such a way that it's completely as accurate as we can possibly be in all of the various aspects of how we're going to embody this data. Below that, we want to expand the work of Liu et al., where we're having the ability to move between models, hardware, at any point in the model's life cycle. So even at a granular sense, we want the ability to move between architectures if it makes sense. So the question here for performers is, why would you move at that stage? What is the resolution? And what is the advantage and disadvantage? And when do you do it and when do you not do it? Okay. And then we want to create machine-readable energy semantics for machine learning, ESML. And this has to be logical first-order predicates. And whether this is a logic like LTL or calculus like a multimutex calculus, MMC, pictured here, however this is done, this is something that we're asking the performers of how we should capture these energy semantics so that we can reason over the electric measurements that we've taken. Again, this reasoning is to discover the interactions so we can constrain that exploration space, making this more computationally feasible. Finally, the toolbox in the bottom is the functions that we're going to consider and selecting those functions that we're going to then create as tunable objective functions. So that's the first 6 months of the program, is setting up this experimentation. And then for the remaining 18 months, we're going to be looking at exploring the energy semantics. So actually running all these experiments, capturing the electrical signals, using the logic that was constrained and reasoning over it. We're going to be exploring multi-objective functions. So this is joules of energy and model performance. So in classification, this would be accuracy, precision, recall, and F1. And to make this a useful product at the end of the program, we want to discover algorithms for creating energy-aware ML, considering the hardware, the data, and where we are in that life cycle, given the previous design decisions, which we're now capturing via energy-aware semantics. All right, so I provided a little basis of confidence that we could capture power, so with the NVIDIA PCAT tool. So I want to provide a little more basis of confidence for the program. Starting on the left-hand side, Condrilli et al. Demonstrated that by using and tuning hyperparameters in a multi-objective function, in this case, they use a Pareto. A small aside, I keep mentioning a Pareto. It is a common multi-objective many people are familiar with, but please by no means take that as a limiting factor. All multi-objectives should be considered. You're free to consider all multi-objective functions. So here, the way we read this chart is the more area under the curve of this hypervolume on one axis, the greater the efficiency of the Pareto optimization. So by doing this for power and performance, just tuning the hyperparameters in this way, they were able to gain a more efficient model. At the bottom, we have the cumulative normal query cost. This is just the total sum of epochs over the different hyperparameters that were tested. So this result shows that just tuning the hyperparameters gives us an advantage. And what we really want to do is change the way we're doing the mathematics for these different objective functions like loss functions. So an example I'll give here is the mixed train paper out of Columbia by Dr. Jana et al. And in this, they changed the loss function to make it more computationally feasible. In this case, they were looking for robustness and using the application of formal methods. But in doing so, they made this more efficient in computation. Moving to the right-hand side, Noah Smith et al. Demonstrated in the branch train merge paper a 40% reduction in GPU usage by training a branch model and then training expert models. So this is effectively a gated mixture of experts without the gate. And yeah, so the way we read this chart is we have perplexity on one axis. So when we're training a large language model, we want to score the accuracy of the next token. Loosely, we can think of this like a Shannon entropy. And they achieve the same perplexity using, in this case, GPU hours, and they use 40% less. So I just want to highlight again that we want to use joules of energy because we want to map machine learning to physics. So we can compare across architectures and other aspects. So this is a good comparison GPU to GPU. But we want to be able to do this from photonics all the way to any other form of hardware. Another interesting finding of this paper is the way we train large language models today is we scrape the internet for text. Turns out on the internet, people say stupid things. And now racist, sexist, bias, and so on. So now we have a model with biases we don't want. So we continue to train it. We use human reinforcement learning to train it. And then we're not sure if we got it all. So now we have guard models on top of this model. What's the electric cost of that data source selection? On the branch train merge paper, they trained their base model on Java code. This will have errors. They will be off by 1, buffer overflow errors, and so on. But then you can fine tune on peer-reviewed papers. How much less electricity do you use by not putting those biases in your data source to begin with? So the data set and the electric cost of this is something we should be considering more in a principled fashion and applying reason to it. All right, this slide takes a minute to explain. And the eighth Hellmeyer question is metrics. So when we want to describe a lower bound, when we're looking at computer hardware, we want to make sure that we have an equal pile of data and we give it to several points of hardware and we see which one does the work fastest, right? So we want to essentially load the system and see how it performs. When we have an efficient algorithm, well, it just does less work because we're more efficient in the way we're doing the processing. When we're testing this, when we're prescribing the lower bound for machine learning, we need algorithms and hardware to work together. So the performers will be required to deliver the what we're calling the machine learning lower bound MLP LinPack, which stands for linear packaging. So the original LinPack paper from Cleve Moeller et al. In 1979, there's been a lot of work on this area over time. NVIDIA offers HP LinPack on their website as one of their benchmarks for their GPUs, which stands for high performance linear packaging. There's also highly parallelized linear packaging. I'll start on the left-hand side. We want to look at what is the lower bound for machine learning for training. So if we have a random matrix and we presume it's perfectly random and we don't have a property of it, and we want to go to a trained matrix, which is a weight matrix, the lowest computation is one touch of every element. We can't do less than this linear transformation if we assume that it's perfectly random to start with and there isn't a structure embedded in there that we're capitalizing on. So the lower bound would be a linear transformation for training, a single epoch. The machine learning lower bound for inference. So if we have, again, a weight matrix, if we think of this like a neural net, just as an example, a single neuron firing, this one vector multiplication is the lowest aspect. You cannot do an inference without at least using one neuron, right? So this is the lower bound for machine learning inference. The shape of the matrix is presumed by the data set, which is an assumption, and the hardware that's being used, which is an assumption. So you're free to use whatever hardware you'd like, but we will require that you give the MLP program a MLB LinPack metric that we can establish a lower bound. So looking at this, just taking a step back, we have a training data set and hardware that these are both assumptions listed in green on the left-hand side. We're going to presume that the machine learning algorithms to marshal the data require zero electricity. Again, we're establishing a lower bound, right? And we compute the MLB LinPack for training and inference, and it's the sum of these electric expenses for the model. So this is not just the graphics card or whatever we're using. It's the computer system, it's the cooling, it's everything that's being used in the system. So at the start of the program, we're going to freeze what is the state of the art. So this is the blue line here. And we're going to compute the HP LinPack for all of the different hardware that is provided. And this gives us a delta, which is the not yet achieved but feasible portion. We can think of this as a power budget or a battery. The bottom line in the table below is at the end of the first year of the program, we want to achieve using less than 90% of the battery or the power budget, and then 75, and then 50. But we also want to have the ability to use the machine learning to physics to build new hardware in the future. So we want to understand when we have a data set, what its power usage will be. So in the top row of that table, we want to be able to predict at the end of year one at 60% accuracy, and then 80, and then 99 without actually building the hardware. So it's these energy semantics and this logical reasoning that's allowing us to make a prediction of the amount of power given the certain hardware that's being used and the data set that's being tested. And then obviously we'll test this against what actually uses to get the delta for the scoring. So this is a single TA. There will be a separate test and evaluation team, which will be a government partner or FFRDC or UARC. We're going to have multiple selects. And I do want to point out that the go, no go in here is an intentional down select. And we'll be using the program metrics for the down select. So just to cover the schedule again, in the first 6 months, we're looking at developing capital F forensic instrumentation, selecting the objective functions that we're going to then create to be tunable objective functions, creating the energy aware semantics, and in the first 6 months, looking at ways to convert trained models or partially trained models to different hardware. So extending the work of Liu et al. Again. But after that first initial 6 months of setup, we spend the remaining 18 months iteratively improving and exploring multi-objective functions. So again, that's joules of energy and performance. And exploring the interactions. So actually taking the measurements, developing the reason, and discovering these interactions that are constraining that objective space. We're then going to develop algorithms. So for a given piece of hardware, for a given task in a data set, we want to construct at any point the most efficient machine learning algorithm. Oh, I should also point out that we're going to be doing code drops every few months. So the data sets, the tutorials, the code, all of this information is expected to be made public. I'll talk about transition path in a few moments. All right. So when the PS comes out, again, everything in the PS supersedes what I'm saying here. But when the PS comes out, we're going to do abstracts. And then by invitation, we'll do oral and written proposals. A few points that I personally just want to point out is please be very clear in your proposal about your open source license, MIT or what license you're using. Please submit on time. Don't wait till the last minute to submit. I have seen this many times, sadly. Imagine something goes wrong and you don't have the time to deal with it. So please submit early. Proposals should define their experiments. Again, there's been many times throughout this presentation where I've kind of described where the performers define these experiments as we're building them. What is valid about your approach? What is the evidence of this? And why that approach is novel. And then finally, in the technical section, please be technical. In the executive summary, you're describing the overview and you're kind of walking the reader into how it works as a whole. But in the technical section, please feel free to be very technical because there's a lot to describe here. So, vision and transition. In the vision statement, we're imagining where the program will be in 10 years, right? So well after the 2-year program ends. In 10 years, I'd like to see MMLP software as the gold standard for machine learning construction and simulation of power usage. Be like the ideal vision here. The impact objective is at the end of the program, what would I like to see? Here, we want the code to be available to the open source community so that people can actually use it commercially, academically, and so on. And So this can be on development sites such as scikit-learn, PyTorch, Keras. There's many others. So we want to get it in mainstream repositories so it's commonly used. So again, the transition strategy is to make this available, and because it has a benefit, people will be using it just to save themselves their own electrical bill, right? So we do expect that the code will be posted open source and also on the DARPA GitHub page. We're going to highly encourage publication. So as new discoveries are made, we're going to encourage publications in machine learning journals, NeurIPS, computer science, IEEE, and others. And we're also encouraging working with the community, such as SOSA or Edge AI Foundation, to make this more available and aware to people who are actually practitioners doing edge machine learning. The end. All right. Thank you all for coming out, and I appreciate everyone's attention.